ton of steel travels 20 miles toward a target moving at 30 knots. Wind, gravity, and the Earth's rotation corrupt every shot. Human brains cannot solve this in seconds, but 5 tons of precision gears can. Discover the mechanical gods that turned chaos into a mathematical slaughter. To understand the sheer impossibility of manual naval gunnery, one must look at the window of time between the flash of the muzzle and the impact of the steel. When a 16-inch gun fires, it launches a projectile the weight of a luxury car into a chaotic laboratory of physics. At a range of 20 miles, this shell remains in the air for over 70 seconds. During this flight time, a target cruising at 30 knots moves nearly 3/4 of a mile from its original position. Firing at the enemy's current location is a guarantee of failure. The crew must instead fire at a patch of empty ocean where they predict the enemy will be over a minute into the future. This prediction is not a simple linear guess, it is a nightmare of converging variables. As the shell climbs to the peak of its arc, miles above the waves, it encounters shifting air densities and layers of wind moving in different directions. A headwind or tailwind changes the drag, while barometric pressure and even the humidity level dictate how much energy the shell loses to friction. If the gunpowder in the magazine has warmed up by a few degrees due to the ship's internal climate, the explosion becomes more violent, increasing muzzle velocity and causing the shot to sail past the target. Even the physical state of the gun itself is a variable. Every shot fired strips away a microscopic layer of the barrel's rifling. This erosion gradually lowers the pressure behind the next projectile, meaning the 10th shot of the day will travel a shorter distance than the first, even with an identical powder charge. Beyond the atmosphere, the very rotation of the planet interferes with the trajectory. The Coriolis effect means that while the shell is in transit, the Earth is spinning beneath it. In the northern hemisphere, a long-range shot will naturally drift to the right of its intended path. Ignoring the Earth's rotation at these distances ensures a miss of several hundred yards. Additionally, because the barrel is rifled to stabilize the shell, the projectile spins at thousands of revolutions per minute. This creates a gyroscopic drift, a phenomenon where the shell leans into its own rotation and curves through the air like a massive, lethal baseball. Synthesizing these factors, environmental, mechanical, and planetary, into 2 final coordinates for the gun turrets is beyond the capacity of a human brain under the stress of combat. A single mathematical error or a slow calculation means a wasted salvo, and in a duel between battleships, the first side to find the range usually wins. The requirement for a hit is the instantaneous solution of multiple nonlinear differential equations. This technical wall led to the creation of the most complex mechanical objects of the mid-20th century. To survive, the Navy had to stop relying on human intuition and start building machines that could translate the laws of physics into the motion of brass gears. These devices were not merely calculators, they were physical simulations of the battlefield, where every variable was represented by the precise rotation of a shaft or the curve of a metal cam.
The challenge of solving these equations in real time required a physical manifestation of logic. In a modern computer, a number is an abstract voltage state in a transistor. But in a 1940s fire control computer, a number is the specific angular position of a rotating steel shaft. To add 2 variables, such as the ship's own speed and the wind velocity, engineers utilized the mechanical differential gear. This mechanism functions exactly like the axle in a car. By feeding 2 different inputs into the side gears, the central carrier rotates at a speed that represents the sum or difference of the 2. This is a primitive but infallible form of hardware-level addition that never crashes or suffers from software bugs. Integration, the mathematical process of calculating distance based on varying speeds over time, was managed by the disk and ball integrator. This device is the pinnacle of analog computing. It consists of a flat, horizontally rotating disc and two small steel balls held in a movable carriage. The disc spins at a constant rate, representing the passage of time. As the input variable, such as the rate of change in an enemy's bearing, shifts, the carriage moves the balls toward or away from the center of the disc. The further the balls move from the center, the faster they are forced to spin by the rotating disc. The cumulative rotation of these balls is the integral. This allowed the machine to continuously track the target's path, essentially building a physical model of the target's future position. Perhaps the most complex components were the three-dimensional cams. These were solid metal shapes sculpted into irregular, flowing surfaces that look more like modern art than military hardware. These cams acted as physical lookup tables for nonlinear functions. For instance, the relationship between a gun's elevation and the actual range of the shell is not a straight line because of air resistance. An engineer would calculate this curve and then carve it into the surface of the metal cam. A follower arm would ride along this surface. As the cam rotated to represent a specific range, the arm moved up or down to provide the exact mechanical output for the gun's elevation. The precision required was staggering, often measured in 10,000ths of an inch. A microscopic imperfection on the surface of the cam could translate into a shell landing 500 yards away from the intended target. These machines were massive, frequently weighing over 3,000 pounds, and were housed in shock-mounted steel cabinets deep within the ship's armored core. Inside, tens of thousands of precision-machined parts worked in a synchronized, silent dance. Unlike a digital processor that handles tasks one after another, these analog giants were massively parallel. Every gear, shaft, and cam moved simultaneously. The moment a sensor detected a change in the ship's heading or a radar ping updated the distance, every related component in the system adjusted instantly. There was no processing lag and no loading time. The calculation was the motion itself. This mechanical speed was vital because in a high-stakes engagement, the delay of even a few seconds in a firing solution could result in the destruction of the ship. The entire process was a continuous flow of rotating brass and steel, turning raw sensory data into a lethal trajectory. Moving into the next phase of the process, these internal calculations had to be converted into the actual movement of massive gun turrets weighing hundreds of tons. This required a seamless link between the delicate gears of the computer and the brute force of hydraulic machinery. The evolution of these mechanical titans reached its absolute zenith through the work of a man named Hannibal Ford. His creation, the Ford Rangekeeper Mark I, became the undisputed brain of the United States Navy's heavy surface fleet. While other nations were struggling with semi-manual calculators, Ford's design stood out due to its exceptional reliability and deep systems integration. This machine was roughly the size of a large domestic refrigerator and contained over 30,000 individual parts, all synchronized to serve one purpose: maintaining a continuous, fluid firing solution despite the total chaos of a naval engagement. The Mark I did not simply wait for data to be typed in. It anticipated the future through a sophisticated feedback loop. This internal logic allowed the machine to verify its own calculations, making it a closed-loop system that was far more stable and accurate than the open-loop designs used by competing navies. A massive technical hurdle was how to get the calculation from the brain to the guns. A battleship is a sprawling city of steel, and the computer sits deep in the hull while the guns are hundreds of feet away. Before this era, transmitting coordinates was a clunky process involving frantic phone calls or manual dial setting, which introduced massive delays and human error. Hannibal Ford solved this with the implementation of the synchro, a specialized electrical transformer. The Mark I converted the angular positions of its mechanical shafts into precise electrical signals.
These signals traveled through the ship's armored wiring to receivers in the gun turrets, which then converted the electricity back into mechanical movement. This allowed the gunners to simply follow the pointer. As the gears inside the computer turned, a dial in a turret located 2 football fields away turned in perfect synchronization. The gunners only had to keep their manual controls aligned with the computer's indicators, ensuring the massive barrels were always pointed at the exact spot in space the machine had designated. The environment inside a combat battleship was an engineer's worst nightmare. When a ship fires a full broadside of main battery guns, the entire hull vibrates with such violence that light bulbs shatter and human eardrums can rupture. The Mark I had to maintain precision within microns while sitting at the epicenter of this man-made earthquake. Ford addressed this by mounting the entire computer on a massive, shock-absorbing base and utilizing hardened steel for the gears to prevent warping under stress. However, calculating the target's position was only half the battle. The machine also had to account for the ship's own motion. This was the job of the stable element, a linked unit featuring high-speed gyroscopes. It tracked every degree of roll and pitch at the exact millisecond of the firing trigger pull. If the ship tilted 5 degrees to the left as the trigger was pressed, the computer instantly adjusted the elevation of the barrels to compensate, preventing the shells from either soaring into the clouds or diving into the waves directly in front of the bow. Manufacturing these devices was a monumental industrial feat that defied the logic of mass production. There were no automated assembly lines for the Mark I. Each computer was hand-assembled by master machinists who treated every gear as if it were a surgical instrument. Testing a single unit involved weeks of simulated battles to ensure the mechanical output matched theoretical ballistic tables to the 4th decimal point. This level of quality control meant that by the time American battleships entered the war, they possessed a level of technological maturity that their adversaries could not match. The machine effectively removed the variables of human fear and fatigue from the equation. While an enemy officer might fumble a slide rule calculation under heavy fire, the Mark I continued to dispassionately grind through the mathematics of destruction, oblivious to the explosions rocking the hull. This technical superiority created a massive gap in capability, transforming long-range gunnery from a game of chance into a systematic execution of a pre-calculated sentence. This mechanical intelligence was about to be tested in the harshest conditions the ocean could offer, proving that in the wars of the future, the winner is not always the one with the biggest guns, but the one with the fastest gears.
The true test of these mechanical brains arrived when theory met the cold reality of the Mediterranean and Pacific theaters. For decades, naval doctrine assumed that night fighting was a chaotic gamble, often ending in accidental friendly fire or total confusion. The Battle of Cape Matapan in 1941 shattered this assumption. British Admiral Cunningham led a fleet equipped with the Admiralty Fire Control Table, the British equivalent to the American system. While the Italian cruisers relied on traditional visual spotting and manual calculations, the British had achieved a level of technical synergy that felt like sorcery. Their analog computers were now receiving direct data feeds from early radar sets. This meant the mechanical ghost inside the ship could see through total darkness. When the British battleships opened fire at a range of less than 4,000 yards, the Italian crews didn't even have their guns manned. The British computers had calculated the solution minutes before the first flash of light. The result was not a battle, but an execution. 3 heavy cruisers were sent to the bottom of the sea in minutes, victims of a machine that never needed to see its target with human eyes. As the war progressed, the sophistication of these calculations reached a level of terrifying efficiency. In October 1944, during the Battle of Surigao Strait, the world witnessed the final duel between battleships.
The American USS West Virginia faced off against the Japanese battleship Yamashiro in pitch-black conditions. The West Virginia was equipped with the newer Mark 8 fire control computer, a machine capable of handling even more variables than its predecessors. While the Japanese ships struggled to find the range, firing flares and searching blindly, the West Virginia's computer had already locked on to a radar blip 13 miles away. The machine translated the invisible pulses of radio waves into the physical rotation of its internal gears. When the order to fire was given, the first salvo of 16-inch shells traveled through the night and scored a direct hit on the very first try. This was statistically impossible for a human gunner. It was the mechanical certainty of the analog computer processing the ship's yaw, the wind's gust, and the shell's flight time in one continuous motion that ended the era of the samurai of the sea. The psychological impact on the receiving end of these calculations was devastating. Survivors of ships targeted by computer-directed fire often describe the uncanny accuracy of the shells. In traditional warfare, a ship would fire a bracketing shot, one long, one short, and then adjust. With the American Mark 37 and Mark 1 systems, the bracketing happened inside the gears before the first shot ever left the barrel. Enemy captains found that their standard evasive maneuvers, such as zigzagging, were often useless. The analog integrators inside the computers were designed to calculate the rate of change of a target's bearing. If a captain turned his ship, the computer sensed the change in the radar data and immediately shifted the gears to predict the new curve of the path. The machine was essentially outthinking the captain, solving his next move before he had even completed the turn of the rudder. This technical dominance redefined the concept of naval supremacy. It was no longer about who had the thickest armor, but who could maintain the most stable mathematical model of the battlefield. The Japanese, despite building the Yamato, the largest battleship ever constructed, never managed to integrate their optics, radar, and computers into a single seamless nervous system. Their fire control remained a fragmented process of humans interpreting dials and then manually entering data into machines. In contrast, the Allied systems were becoming fully automated fire-and-forget loops. This mechanical evolution reached its peak when these systems were forced to pivot from the slow, lumbering targets of the sea to the screaming high-speed threats descending from the sky. The gears that had conquered the ocean now faced a new, much faster enemy that pushed the limits of analog physics to the breaking point. The transition from targeting 1,000-foot ships to tracking nimble aircraft required a radical redesign of the mechanical architecture, leading to a new generation of predictors that had to work 10 times faster.
The shift from naval duels to aerial defense changed the fundamental nature of mechanical computing. A battleship is a massive two-dimensional target moving at 30 knots. A dive bomber is a tiny three-dimensional streak of lightning moving at 300. The time available to calculate a firing solution dropped from minutes to mere seconds. To meet this threat, engineers had to shrink the massive power of the Rangekeeper into compact, portable units like the British Kerosene Predictor and the American Mark 37 system. These devices were tasked with solving the lead problem in a sphere of total motion. Not only did the computer have to predict where the plane would be, but it also had to calculate the exact fuse timing for the anti-aircraft shells. If the shell exploded 10 feet too early or too late, the blast was harmless. The gears now had to output a three-dimensional coordinate and a time delay simultaneously, updating several times every second. This era saw the birth of the close-in defense logic that still exists today. The most remarkable technical achievement was the integration of the analog computer with the proximity fuse. Before this, a mechanical timer had to be set by hand on every single shell based on the computer's output. But as the speeds of German Luftwaffe and Japanese kamikaze aircraft increased, the human hand became the weakest link. The solution was a revolutionary hybrid. The shell itself became a miniature sensor, but the brain on the ship's deck still did the heavy lifting. The analog predictors would use radar to lock onto an incoming target, and through a series of high-speed mechanical differentials, they would guide the massive 5-inch guns to spray a curtain of steel in front of the aircraft's path. The computer wasn't just aiming at a point, it was calculating a volumetric kill zone, managing the high-speed ballistics of thousands of rounds fired in rapid succession. The peak of this technical desperation was the defense of London against the V-1 flying bombs. These were the world's first cruise missiles, fast, low-flying, and relentless. Human gunners were almost entirely ineffective against them. In response, the Allies deployed the SCR-584 radar coupled with the Bell Labs No. 10 electronic analog predictor. This was a transitional masterpiece. It used vacuum tubes to handle the initial electrical data, but relied on high-speed mechanical servos to physically point the guns. This machine could track a V-1 at speeds exceeding 400 miles per hour and calculate the intercept point with such precision that the success rate of the anti-aircraft batteries jumped from 10% to over 70%. It was a mechanical wall built of logic and brass, stopping the first robot weapons with the first robot hunters. However, as the jet age dawned, the physical limitations of metal began to surface. A gear can only spin so fast before centrifugal force or friction causes it to warp or seize. To track a jet moving at near sonic speeds, the internal shafts of an analog computer would have to rotate at tens of thousands of revolutions per minute, speeds that would turn the precision lubricant into smoke and melt the brass bushings. The machines were becoming victims of their own mechanical nature. Engineers were forced to push the tolerances to the absolute edge of what metallurgy allowed, creating systems that were so complex they required constant specialized maintenance just to stay calibrated. The hunt for speed was reaching a physical ceiling where the weight and inertia of the gears could no longer keep up with the weightless flow of electrons.
The pursuit of absolute mechanical precision was an endeavor that bordered on the obsessive, pushing 20th century metallurgy to its breaking point. To build a machine like the Ford Mark I, an industrial ecosystem of unparalleled skill was required. These were not products of a standard assembly line. They were the results of thousands of hours of hand filing, polishing, and individual calibration. Every single gear had to be cut with a tolerance of less than 1/10,000th of an inch. If a shaft was slightly misaligned, or a tooth on a differential had a microscopic burr, the cumulative error through the chain of 30,000 parts would result in a firing solution that missed by miles. This created a massive bottleneck in production. While a factory could churn out thousands of rifles a day, it could take months to complete a single fire control computer. The world's greatest navies were essentially dependent on a handful of master clockmakers who had been retrained to build instruments of war. The maintenance of these machines was a constant battle against the elements and physics. A battleship is a humid, salt-aired, and vibration-heavy environment, the literal opposite of a clean room. Salt air is a corrosive agent that can pit the surface of a brass cam in weeks, changing its mathematical output. To counter this, the computers were housed in pressurized, climate-controlled rooms, and the internal components were bathed in specialized oils that had to maintain a constant viscosity, regardless of whether the ship was in the freezing Arctic or the tropical Pacific. If the oil thickened in the cold, the friction would slow the rotation of the shafts, introducing a lag into the calculation that could cause the guns to trail behind a moving target. Technicians lived in a state of perpetual vigilance, using sets of master gauges to check the alignment of every critical gear every single day. A dropped gear or a loose set screw was treated with the same gravity as a hole in the hull. Beyond the physical fragility was the problem of data rigidity.
An analog computer is a hardwired logic gate made of metal. If the Navy decided to change the type of propellant in their shells to a more powerful mixture, the entire computer became obsolete overnight. The ballistic properties would change, the shell would fly faster and flatter, but the three-dimensional cams inside the machine were still carved to the old trajectory. To update the system, the ship had to return to a shipyard, where teams of specialists would physically open the massive steel cabinets, disassemble the core, and swap out thousands of hand-carved cams for new ones. There was no software update in the 1940s. There was only the painstaking replacement of physical hardware. This made the logistics of technological improvement incredibly slow and expensive, tying the ship's lethality to the specific mechanical configuration of its steel brain. The cost of this perfection was not just measured in money, but in the extreme specialization of the crew. A fire control technician was among the most highly trained individuals in the military, requiring a deep understanding of both advanced calculus and heavy machinery. They had to be able to hear when a gear was wearing down or when a servo motor was struggling against a misaligned shaft. This reliance on a small elite of technical wizards meant that if the fire control room took a direct hit, the ship's primary offensive capability was effectively neutralized, even if the guns themselves were untouched. The machine had become the single point of failure. It was a masterpiece of the industrial age, a peak of human ingenuity, but it was also a dead end. The complexity had reached a plateau where any further increase in performance would require the machine to be too large to fit in a ship or too delicate to survive a blast. This era of perfected metal was about to collide with a new invention that promised the same logic without the weight of the gears. The transition would be slow, but the first cracks in the analog monopoly were appearing as the world entered the age of the transistor.
The transition from gears to electrons was not an overnight revolution, but a long hybrid twilight that lasted well into the 1970s. As the jet age and the missile era arrived, the sheer speed of combat began to outpace the physical inertia of rotating metal. However, early digital computers were fragile, massive, and prone to overheating, hardly suitable for the violent vibration of a firing deck. This led to a fascinating period of hybrid engineering. In the 1950s and 60s, systems like the ones guiding the first Terrier and Talos missiles used a mix of vacuum tubes for high-speed logic and mechanical servos for the heavy lifting. The analog computer didn't disappear, it evolved. It became the interface between the ethereal world of radio waves and the physical world of steering a 5-ton missile. This era saw the final, most ambitious act of analog logic, the Cold War's ballistic missile race and the early space program. Even as digital processors like the Apollo guidance computer began to emerge, many critical flight systems still relied on analog principles for their instantaneous response times. In the world of supersonic flight, the Lockheed SR-71 Blackbird utilized an air data computer that was a marvel of miniaturized mechanical complexity. It had to translate the pressure of the air rushing past at 2,000 miles per hour into mechanical movements that adjusted the engine inlets. At those speeds, a digital glitch or a millisecond of processing lag could lead to an unstart, a violent engine failure that could rip the plane apart. The mechanical system, with its direct physical link between the sensor and the actuator, provided a level of real-time reliability that early digital code simply could not guarantee. By the 1970s, the silicon revolution finally began to close the door on the era of brass and steel. The invention of the integrated circuit meant that the work of 30,000 gears could now be performed by a few slivers of silicon no larger than a postage stamp. The massive refrigerator-sized cabinets deep in the hulls of ships were replaced by racks of silent, glowing electronics. The physical 3D cams, which took months to carve by hand, were replaced by digital lookup tables stored in magnetic memory that could be updated in seconds with a new reel of tape.
The steel brain was dying, but its DNA was everywhere. The algorithms we use today for predictive tracking, the way your smartphone camera follows a face, or how a modern drone stabilizes itself in a gust of wind, these are the direct digital descendants of the differential gears and disk integrators of the 1940s. The end of the analog era was marked by the decommissioning of the last great battleships. When the USS Wisconsin and USS Missouri were reactivated in the 1980s, they still carried their original mechanical Mark I computers. Even in an age of satellite GPS and Tomahawk missiles, these analog relics were still so effective at calculating the ballistics of 16-inch shells that the Navy saw no need to replace them. They stood as a testament to a time when engineering was something you could touch, hear, and smell. The shift to digital brought more power and less weight, but it also removed the transparency of the machine. You can no longer watch a digital processor think, but you could stand next to a range keeper and watch the gears spin as it solved the geometry of a distant horizon. As we move toward the final chapter of this story, we look at what remains of this incredible period of human creativity. These machines were the peak of a specific kind of genius, a bridge between the industrial past and the digital future.